Ask most people what they know about physics, and you'll probably get an answer like, it's hard with lots of math. Well, this can be true, it really misses what physics is all about. Physics is about problem solving. And while this includes a math aspect, I really believe what makes physics so difficult to so many people is just figuring out what the problem actually is and how to go about solving it. So here we're going to go through some kinematics problems. I want to emphasize, though, that this is not an exhaustive list of sample problems. There's absolutely no way for me to give you an example of every type of problem that you're going to come across. The secret to doing well in physics is being able to understand the underlying concepts and apply those to different situations. So let's start with a simple one, shall we? According to the Department of Transportation, checking a text message takes on average 4.6 seconds. If you are driving with a velocity of 32 meters per second, how far have you driven with your eyes off the road? So you always start by writing out everything the problem gives you. In this case, we know the velocity of the car and the time the car travels. Since no other indication is given, we can assume that the car is moving with a constant velocity. Lucky for us, we have developed a mathematical model for constant velocity. We know that the velocity of an object is equal to its displacement divided by its time. Looking at our problem, we are trying to find out how far the car travels, which, assuming the car is moving in a straight line, means we are looking for the displacement. We need to rearrange our equation to solve for displacement, so we will multiply by time on each side. From here, we can simply plug in some numbers. The velocity is 32 meters per second, and the time is 4.6 seconds. Now again, in absence of any other information, we can just say that this is a positive velocity. It's really simple to just say, okay, at the beginning, everything's going to be positive. And then if something changes direction, we can go in and add a negative later. So it doesn't matter which direction we are driving. We're driving in a straight line with a constant speed, so our velocity is going to be constant. And we can define that as positive. Multiplying those two numbers together, we get 147.2 meters. Now notice in the problem we have a label with meters per second, and we multiply that with a label of seconds. A seconds label in the numerator and one in the denominator will cancel each other out, and we are left with the meters. Now also notice how many significant figures we have in our answer. There are 4, which is too many, because looking back at the values in our problem, we see the velocity has 2 and the time has 2. So we really want to round this to 2 significant figures. This will give us a displacement of 150 meters. Note that the 0 here is not significant because there is no decimal place after it. So only the 1 and 5 are significant. Now let's look at this from another perspective. We still take 4.6 seconds to check our text message. And we are traveling with a velocity of 100 kilometers per hour. And we have a deer that has wandered out onto the highway 115 meters away. Do you hit him while checking your phone? All right, so again, start with what you know. We know the velocity of the car, we know how long it will take for you to check your phone, and we know how far away the deer is from the car. Now, there are a couple different ways we could go about solving this problem. We could figure out how long it takes us to stop just before hitting the deer, or we could figure out how far we are going to travel in the time our eyes are off the road. Before we do that, though, let's look at our knowns a bit more. Our velocity is in kilometers per hour, while the time is measured in seconds and the displacement is measured in meters. The first thing we want to do is convert one or more of our values so that everything is in the same units. To do this, we need a couple conversion factors. So let's start with the kilometers. We want to convert that into meters. Kilo means 1,000, so there are 1,000 meters in 1 kilometer. Since kilometers is in the numerator of our original unit, we will use the conversion factor that has kilometers in the denominator. This will cancel out kilometers and leave us with meters, which is exactly what we want. Then we want to convert the hours into seconds. There are 3,600 seconds in every hour. Since hours is in the denominator of the original unit, we want to use the conversion factor that has hours in the numerator. This will put 3,600 seconds on the bottom. Now our hours have canceled out and we have been left with meters per second as our overall label. To calculate, we simply take our 100 times 1,000 and divide by 3,600. This gives us a velocity of 2.77777 meters per second. Now, one thing to keep in mind when rounding. The more you round, the more your final answer will be off. The more steps you have in a problem, the more rounding, the more error you introduce. So since this isn't the final step in our problem, we probably want to keep it as all of those 7s until we get to the end. All right, so back to our problem. One way we could solve this problem is to determine how far the car travels in the given amount of time. This is just like our first example in that we are going to take our equation for constant velocity and rearrange it to solve for the displacement. We just converted the velocity to 27 meters per second, and our time is still 4.6 seconds. Solving for this, we find the car travels 127.777 meters. It's a day for 7s. Looking at our problem, each of our knowns were given with 3 significant figures. So we would want to round to 128 meters. Unfortunately, our deer was only 115 meters away, and so we collide. Now, another way to approach this problem is by looking at the time. We know that the deer is 115 meters away, so we can determine the amount of time it takes for our car to stop in that distance. Take our distance of 115 meters and divide it by our velocity of 27, and we find that it takes 4.14 seconds to travel 115 meters. Since we are not responding for at least 4.6 seconds, we don't look up in time and smash him to bits. Now, what if we do hit the brakes at the time that we see the deer 115 meters away? At what rate is the car going to need to accelerate in order to not hit the deer? Well, what do we know? We know the car is traveling with an initial velocity of 28 meters per second. And we know that we want the final velocity to be 0 meters per second. We are given the average time it takes to check a text message, and we know that the deer is 115 meters away. We also know that the car is no longer moving with a constant velocity, so the equation we have been using will not get us what we need. Now, we do have 3 equations that describe accelerating motion, but which one should we use? We're wanting to solve for acceleration, which all of them have, so that doesn't narrow it down at all. This first equation needs the final velocity and the initial velocity and the time. So at first glance, this might be the one to use. But let's think about this time for a second. In the context of this equation, the time would be the total time that it takes for our car to go from 28 meters per second to a complete stop. Is that what this 4.6 seconds is referring to? It's really not. The 4.6 seconds is the amount of time we are not looking at the road, which we determined in an earlier problem to not be enough time to stop the car. So really, we are not able to use this equation because we don't know how long it will take to stop the car. What about this second one? We know we need to stop before 115 meters, so we know delta x. We are looking for the acceleration, and we know our initial velocity. Still, though, we do not know time, and in this case, we need it twice, so no good there. But we've got one more shot. This last equation needs the final velocity. Check. The acceleration is what we're looking for. We know the displacement, and we know the initial velocity. Nice, so let's use this equation. Now, our acceleration is buried in the middle of this equation, and we need to get it out. The initial velocity squared is added on the right, so we need to subtract it to get it over there with the final velocity squared. Then we can divide by 2 and divide by the displacement to get our acceleration by itself. From here, we can plug in 0 for our final velocity and 28 for our final velocity. Notice that this will give you a negative number. Then divide by 2 and divide by 115 meters. Plugging this into the calculator, we will get negative 3.408695652. The lowest number of significant figures in our problem was 3, so we will round to 3 numbers, giving us a negative 3.41 meters per second squared. So does this number make sense? What is the negative telling us? We are moving in the positive direction and we are slowing down, so we definitely should be getting a negative acceleration. So let's go back to our time. How long will it take the car to come to a complete stop? Now remember, we just found acceleration, so we can use that in our problem. And we know the initial and final velocity, so we can actually use this first equation. So we need to get the time out of the middle of that equation. So subtract the initial velocity and divide by the acceleration, and then we plug in what we know to find 8.21 seconds.